Hello, my name is Juan Blond, and well, I will talk about something different. What we have seen here today, it's well, it's different. I hope that you will like it. Well, before we begin, I would like to acknowledge my colleague Oriol Rios. It's sitting there, so the difficult questions, please, in this direction. So we will talk about how to simulate a premixed flame, and this work is based with so it's prepared and it's based on our hot smoke testing system, Izar. So the first question is the introduction. Don't worry, it won't be long, but that's the point. So it's based and it's a work focused on our smoke testing system. It was developed by my company, by Basler and Hofmann. We are based in Zurich. And the main results were presented in my thesis in 2013 within the FEMTC program. And what's Izar? So, I mean, I need to tell you what's that. I'm very happy with your question. So, Izar is a gas burner. It's a system with a gas burner, a gas supply system, portable, and, well, some fog smoke generators, because when I told my boss, yeah, we won't have smoke, you won't be able to see anything, he told me, well, try to figure out how we will sell it, and we just need to put some smoke generators. So, I hope that you are thinking that Izar is definitely a cool machine, because it doesn't generate soot. So many of you, I'm sure you have experience with smoke test, and well, one problem is to clean after. That's like no one. We can control the heat release rate from the system at any time, so we are able to follow some fire curves. So that's something cool, and we have a validate FDS model for the system. So please keep following the presentation. So how is that we decide to combine FDS with Izar? Well, smoke tests are done in rooms which are in use or just about commissioning, and we have some limiting factors like the sprinklers, the lighting, everything. So if we come here in this room and we will have to do a smoke test, I think that the Melia people won't be happy if I cross all these lights and I damage the ceiling, etc. So it was definitely necessary to know what will happen, because we are working with premixed flames, and we had no idea which temperatures we could expect above the system. So it's not the best idea to burn the room, and I need to figure out how to avoid it. So I hope that you think that was a good reason to work with FDS and try to know what will happen. Our aim was to calculate the plume temperatures originated by the system, and the temperature is definitely one of the main factors when we are doing a hot smoke test. So realistic test mean high temperature, or the higher possible temperature. So if we want to do a hot smoke test and we want to represent the reality during a fire event, we will have very high temperatures. It's clear that we cannot reach these temperatures, but we should try to be so close as possible. And well, we needed to know to obtain different temperatures for different powers from the system and for different room heights. How to calculate these temperatures? So the combustion efficiency is one of the most things, the best qualities from these premixed flames. But what happens after? So premixed flames are used in closed systems like a boiler or engine or this kind of systems, and no one cares which is the plume generated at such a system, because it's normally contained in a room, so no, not in a room, so in a space, in an engine, and no one cares. And we decided to study what may happen with FDS. So at this point, I think it's necessary to say I began working in this project in January, and they told me, well, we will receive the machine sometime in April or in March, or just try to think what will happen. So yeah, so I had no machine to do tests. I had nothing. So I only had a computer, a system with some properties that I knew from the fabricant, and that's what I had. And what's for me important when I began? So what's for me important? So important, it's not the efficiency. So I knew I had this kind of flame. I knew that the system was very efficient with the combustion, and that was not so important. What's important for me was the smoke, the plume that I will generate. And I defined 3 initial factors. So the species, the temperature, and the origin surface. That's these 3 things. That were 3 things that I knew I could define from the very beginning. As I said, so we are having a premixed flame. We can regulate the amount of gas that we are putting in the system, and we can regulate the amount of air. So we can obtain stoichiometric conditions. So just some chemistry from the school, and you can just know what you will obtain. So you can calculate the products that you will obtain. This combustion product is what we normally say that's the smoke, but we won't see this black smoke. We will just see something transparent, and that's the combustion product. If we just define the mass ratio fuel products, so we can that's just an example. We know that if we want to achieve this 500 kilowatts, we know the heat of combustion from the propane. We are working with propane. I think I didn't say that before. We are burning propane here. We can just calculate how many grams of fuel do we need to maintain this power, and we can just easily calculate the amount of products that we will obtain. The second factor was the initial temperature. So we are releasing, we have a flame, we have a propane flame, we have a premixed propane flame. So we can find in the literature some values. So we can find the values for these combustion temperatures, and we define the flame temperature as the adiabatic temperature. That's this around 2,000 degrees, and that's the second initial factor that we can also find in the literature. And the third factor was so like in any other FDS model, how to define the grid, and how important was that, because we also knew that that's a rectangular surface. I knew that the combustion will take place in this rectangle. I knew the geometry, so I had to consider, I had to simulate, to model this geometry in FDS. We knew that was this 1.2 meters long and something like 70 centimeters wide. So after some proofs, it seems that the 6.5 centimeter cell works well for this system, and it's capable of reproducing this initial geometry from the combustion chamber. It's a view, and yeah, that's something that we obtain from the producer. The last point was, well, what's with the radiation? So when you are doing an FDS, so one of the things is to define this radiation fraction. How will that affect the system? Well, it's possible to calculate the radiation considering the partial pressures from the products. Intuitive, when you have a premixed flame, you have a good combustion, you are not generating soot, the radiation from this flame should be very, very, very low. That's what's the intuition. And we are capable to calculate it with the partial pressures, and it comes to be something like 3%. So we can see that, but I mean, the equation you can find in my paper, that's me, that's my hand, that's something like 20, 30 centimeters, and that's the system working at, let's say, 800 kilowatts, something like that. If you try to do that with a normal fire, so a natural fire diffusion flame, you won't be capable to stay there to someone to take your photo. So it does work. Well, no. Next. Well, at this point, I think that you are probably thinking, it's nice, it seems interesting. If I have more cool pictures, there are some more. And I also have the results. But first, so a cool picture, that's how it looks like. So that's the combustion products, that's the slice, the temperature slice. When we are working with that was the 100 kilowatts model, and that's the one working at 1.2 megawatts, so 1,200 kilowatts. So you can also see the difference. And according to the manufacturer specifications, with the 1.2 we should have a flame about 1 meter high, 1.1, something like that, and it works. That's something like 1 meter. That you can see that the hot region represents what should be the flame, and that's the point of this, to illustrate that how it was built. So let's begin with the plume. Using the combustion product, we can just calculate for its possible power, its possible range of work of the system. I just programmed a temperature measurement. So you have to remember that my aim was not to burn the room, and for me it was really important to know which temperatures could I expect at the very beginning when the plume is direct against the ceiling, in order to avoid any damage there. So I just create, so that's the good point of working with a computer model like FDS, that you can ask for so many measurements as you want, and they are free. So you don't need to pay for the lab hours or the equipment or whatever. And so this way of simulating the system like a source of hot combustion product was also a way of avoiding the uncertainties related with the combustion that every computer model has. So that was also a positive point from this way of modeling the system Izar. We, using the previous described the size grid, this 6.5 centimeters, we had a surface 1.3 meters and this around 20 centimeters, so 19.5 centimeters. And we needed you need to put so the input, you need to give it in kilograms per square meter per second. That's not a big issue. You know the geometry, you know the amount of product that you have. And the first experiment, or the first model, was just doing like a free plume. So all the boundaries were open, and let's see what happened. And it looks like that. So like we saw before, you can see that there is a hot region, which represents what the flame should be. The hottest temperatures can you find there. That's this adiabatic temperature. That's the injection temperature of the gases in the system, and it looks like that. And well, next thing was, okay, let's see if it does work in the reality. So at some point came the machine, and we were capable of doing some tests. So switch on the machine, do some real fire, measure the temperatures in the plume. We decided to use this grid just to measure the central temperature, right? Just to measure the central temperature and two temperatures following this X-Y axis, and some action out of the office, which is always welcome. And we went and we begin with the measurements. We just take a thermocouple, we just take one of these elevators, and we were just taking measurement at different heights and different positions with different powers. And well, we just try to measure we measure many of the possible powers of the system in order to compare with our previous computer results. And it works. So here you can see the temperatures of, the temperatures obtained in the, so along the both axes with the central temperatures, and the comparison between the results, so the simulation and the full scale test. And it works for 1.2 kilowatt, that's the highest power. It also works for 400 kilowatts, and it works also for the 100 kilowatt, that's one of the lower working ratios of the system. And well, the next question was, okay, so we have a model for the plume. So if we have a model for the plume, it should be, we have proof that the plume model works. Therefore, it should be possible to model a full-scale test from the system. And the question was, it was really possible to model this full-scale test. And yeah, it works. So we also did, we take some measurements. We set the system, and we recorded the temperatures at 5 meters, 10 meters, and 20 meters from the system. And we were covering a distance of 2.25 centimeters below the ceiling. That's the model. So that was a very big industrial hall. That's where the system was. And that's the results. I know you cannot see too much, that there are just 3 examples. That the temperatures obtained during the fuel scale test and the temperatures obtained from the model, they match. They looked similar. Some conclusions. This methodology is an efficient tool to model our system. We need the 3 inputs: the combustion products, the flame temperature, and the combustion region. And FDS is capable of solving this turbulence and entrainment around the plume, because so if we have the central temperatures match, that's the result of the entire turbulence and entrainment process. So that's, for us, that's the confirmation that the system works. Yes, some future work, it will be nice to try different configurations, not just the rectangular, but square or whatever, any other possible configuration. Try with other fuels. We are working with propane. We did some tests in the tunnels, but it was not possible also to make the comparison with FDS at this point. It would be nice to have some plume equations for these premixed flames, like we have for the diffusion flames. And it will be also nice to try the new subroutine, the new submodel that now you can find in FDS and see if the results are more or less the same. And just the last thing, so could be that's the future of the FDS simulation. That's too optimistic. Don't take so strength, but we think that it could be possible to validate the FDS geometries a priori. So if we have a premise like a tunnel or a big mall or whatever, and a new use is planned, and if we don't know if the ventilation system will work or whatever, we may carry out a test, take the measurements. With these measurements that we know that we have a validated model for the system, we may validate the geometry, and after that we will work with the design fire. We think that that should help to reduce some uncertainties related with the geometry, and it could be useful to optimize the smoke extraction system. And well, thanks for your attention. And that's
Any questions?
I think you said at some point that you're assuming the radiative fraction is 3%. How did you come to that number? Because it seems very low.
with the you can calculate it with the partial pressures of CO2 and oxygen, and with the temperature, with the flame temperature, you can calculate it. So the equation, it's in my paper. You can find it. So
Okay. All right, I'll take a look at it, because even a natural gas flame is typically, even a small one is about 10 to 15%. So 3% is very low for radiative fraction. The other question I had is, when you measured the plume temperatures, it appeared that you had thermocouples in one quadrant. Is that right?
during the real scale,
The real scale.
we just had one, and we just had to move it. So we were just recording we just set the system
Okay.
at the steady state,
Okay.
and we were just recording its. I think we were measuring for 3 minutes per point
Okay.
in order to
Okay.
obtain a range.
Did you move it on both sides of the
Yeah.
center line?
Yeah,
Okay.
that's what we did.
Okay, because it appeared from your slide that you were only measuring on one side. And I know from doing full-scale experiments,
No.
the plume is never straight up.
Yeah.
It always leans a little bit one way or another. So it's good that you measured different locations.
Yeah.
Okay.
We were measuring different locations, and we were just moving them.
Okay, thank you.
So.
Any other questions? Okay, well, thank you very much for now.